Okay, let's start now. First of all, I think sorry for keeping you all waiting. I have just now seminar to attend. Okay. Now, we have looked at this Rayleigh-Ritz method. So, and there is one example here that I would like you to go through, and this, please go through this so that you are familiar with how to actually use Rayleigh-Ritz method to solve for P critical. So this is, the question is given to you, a cantilever. So this is just like a cantilever column, but it is put sideways. Then it's subjected to a axial force at the free end. Then you're asked to use the Rayleigh-Ritz method to determine the P critical. And in the Rayleigh-Ritz method, you have to make assumptions about the assumed buckle shape. So this is a slightly bent configuration. So it is given here, you have to use this function as the assumed buckle shape and carry out the Rayleigh-Ritz method procedures to determine what is the P critical. Here in this example, this is Y, as we have seen, and Z is actually the axial direction. Okay, so this is X or Z here, and this is Y, and this is assumed displacement field that we are asked to use. Okay, so please try to go through this and get the bending energy and get the potential energy related to for the axial load acting. Be familiar with the expression that you have to use. What is the equation that you have to use for bending energy is similar to what we have covered in EAS661. And the other one is potential energy of the axial load. What is the equation that you need to use? Okay. So that is Rayleigh-Ritz method. And today we would like to go to this particular method. Okay, which is matrix method. Okay. So matrix method is also an energy-based method. And I think matrix method, as we go along, you're going to see is similar to what is being covered in EAS661. Some of the matrix that we use here is similar to the finite element method in EAS661, for those of you taking EAS661 now. So stiffness matrix method. So here the detailed content can be found in section 2.13 of the book by Charges. Okay. And also section 2.14. Section 2.13 is more like the intro, looks like explanation about the basic idea of stiffness matrix method. And 2.14 is on specific applications to the case where there is axial force. And how do we apply that to solve for P critical? So now the basic idea is of stiffness matrix method is you divide the problem that we want to solve. It's similar to finite element method. Is for a given problem, we divide them into elements. So as shown here, we take the example of a fixed beam here, and the actual size of the length of the element is L. But in stiffness matrix method, we divide them into two parts, as shown in this diagram here. The lower part, we divide them into two parts, and then for each of the parts, we have a standard element stiffness equations, where it is shown in this stiffness equations. And element stiffness equation is basically relating the Q, which is the nodal forces, to the delta here, which is the nodal displacement. So this is element stiffness equations relating. It can be either one of these elements, they are the same. So Q is the external nodal forces. It is acting at what we call the node at one end here, one at here, the other one at the other end. Okay, so you can see the Q and also the corresponding delta. And they are related together by these stiffness equations. Okay, and the matrix here is what we call the stiffness matrix. Okay. So element forces, so we call this vector element forces, and we call this vector delta element displacement. Okay. So equation section 2.13 talks about in general when we want to solve a problem like this. So this is not a problem of subjected to axial force. There is no axial force applied in this case. So this is section 2.13 talks in general about the method itself that we can apply to solve for flexural problem. So this is a member which is subjected to the load P at midspan here. This member will bend. So we can solve this using stiffness matrix methods. Okay. So what we would like to see in our EAS663 here is to extend further these element stiffness equations to include the effect of the existence of axial force. Okay. So when we have, okay, then before that, there are some standard procedures that you must be aware of, which is you have element stiffness equations, which is applicable to each of these elements. So if we have 4 elements, if we have more elements here, then we will have 4 sets of equations representing each of the element. So in this example, we take 2 first. So this is representing the problem that we want to solve. But in order to solve this problem, we are not solving this problem, but we start from here, start from the stiffness equations. We want to solve this problem. We must combine all these elements, their equations together to get what we call the structure stiffness equations. Okay. So here we show the structure force and displacement rotations. So this is at structure level. This is actually what we want to solve. Given the forces acting at what we call the nodes here and the corresponding displacement or rotation that will happen at the nodes, okay, we combine all the element stiffness equations into this structure stiffness equations. So instead of Q, which is the element force, we have W, which is the structure load. And it is equal to the big matrix K, that is the structure stiffness equations, multiplied with delta. And delta, instead of the displacement vector at element level, it becomes the structure displacement. And the big K here is called the structure stiffness matrix. So if you solve these equations with this given, this one we can form it. We can form it because there are standard content that we can use, and then we can go through the process that we call assemblage process. From the small k get to big K. That is one of the process that we have to go through. So it is called the assemblage process, starting from the element stiffness matrix, combine them into structure stiffness matrix. So that is the matrix that we know. So the only unknown that we have here is delta. So we can solve this. With W given K, we can form. Delta is unknown, so we can solve for this. So later, when we know the delta at the structure level, we can go back to the element level and find the element forces, for example, shear force or bending moment. So this is a basic idea of stiffness matrix method. Okay. And Okay. Now, if we now extend it to the case of just now, we are looking at beam problem, bending problem. Now we look at a problem that we want to apply this stiffness matrix method to, a problem of a column subjected to an axial load. So in a similar way, we want to solve this using stiffness matrix method. So this column is x-axis in the member axis direction, and there's a y-axis here. And the length is L, and the rigidity is, bending rigidity is EI. And we divide this into two equal parts. So we divide this into two equal parts. So each of them length is L over 2 because the total length is L. Then at each of the so-called nodes here, nodes A, node B, and node C, we have the corresponding structure force or structure load, which is represented using W1, W2, W3, W4, W5, W6, and the corresponding structure displacement, which is represented using delta 1, delta 2, and then you have delta 3, delta 4, delta 5, and delta 6. So this W1, W2, we use the same symbol. So W1 is represented by this arrow here. So it is a kind of force. And the corresponding W3 and W5 also, these are forces. So these are actually the load acting in terms of forces. And W2, W4, and W6, which is acting at the same node together with W2 together with W1, W4 together with W3, W5 together with W6. These are actually applied moment. Okay? So we use the same symbol to make it the same, but they are representing different nature of load. And the same way, the corresponding displacement, delta 1 is the displacement in y directions, but delta 2 here will be the rotations. Delta 3, the displacement at this node here, delta 5, the displacement, but the corresponding delta 2, delta 4, and delta 6, these are rotations. Okay, so these are at structure level. Okay, the corresponding loads and displacement. Now we break down into element. So when we break down into elements, then each of the element also has the element force, nodal force, which is representing with small letter now Q1 for forces, Q2 for moment. Then next at the other end, Q3 for forces again, and then Q4 for moment at the other end. The same thing for the displacement. Delta 1 is for nodal displacement of the element at this node. Delta 2 is the rotations, delta 3 is the displacement, and delta 4 is the rotations. So this is at element level now, using different symbol. And the same thing will happen to the next element. But in order to differentiate from this to this, we start with delta 5, and then delta 6, delta 7, delta 8, and the same thing Q5, Q6, Q7, Q8. So these are at element level. Okay. And now we would like to make it clear the positive directions for the displacement and also the force. So this is the axis X, this is axis Y. Okay. And for positive directions that we assume here in our derivations to get the equation is positive direction is defined as direction negative in negative y directions. Okay. So if we have the X and Y, this is X and Y, and this is the X, this is a Y, this is the X, and this is the Y. So the positive for displacement either the capital delta 1 or the capital delta or the small letter delta 1 there is in the negative direction of y. Okay. X will always be the axis directions from the starting point to the end point, from the starting point to the end point. And y will be in this direction. So the positive one as shown in this arrow is defined in the direction opposite to y. Okay. And for rotations, it is clockwise. Clockwise as positive. So clockwise as positive, here also clockwise, 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 clockwise. So this is the assumption of positive direction of displacement, positive direction of rotations. This is especially important when we have members which is not oriented in the same direction anymore. For example, one member like this, one member like this, one member like this. So it is important for us to understand how we define the positive direction for displacement and rotations. So for stiffness matrix method, in order to consider this effect, we must add to the stiffness matrix, the normal stiffness matrix that we have for beam problem. We need to add a stiffness matrix which accounted for the effect of this axial force. Axial force, especially in compression or tension, has effect on the stiffness. When you have compressive axial force, it tends to reduce the stiffness towards lateral load. When you have axial force which is in tension direction, it tends to increase the stiffness to resist lateral force. So this is the one that we have to consider. Okay. Now, this is the normal one, which it is suitable for the case where to analyze a bending problem, where there is no axial force present. So this is the element stiffness equations, and specifically the element stiffness matrix. This is at element level. We use a small k here for element level, and this represent matrix. Ij means at row I, column J, and this is a four row, 4 column matrix. 4 row and 4 column, and these are the content. Okay. And here symmetry means the row here is replicated here as a column, the row here as a column, the row here as a third column, they are the same. So this means symmetry. Okay. So this can be used to solve problem which is subjected to load like a beam, okay, beam. Okay. In order to extend this to the case where you have axial force acting, for example, in general, beam column, if we want to analyze beam column problem, then we have to add to this stiffness matrix another terms which accounted for the effect of having axial force, compression. We are talking about compression. So here, this is the general stiffness matrix. It can be at structure level. Q is the external force, and then delta is the displacement. And this matrix, if you can see, we add another one which accounted for the effect of compression force on stiffness. So the first one is the conventional one, which is for members subjected only to flexural loads. And the second one is stiffness matrix accounting for the effect of axial load P on stiffness of a flexural member. Okay. And in order to apply this method to determine critical loads, we use the condition for non-trivial solution, which is to get P critical, then the determinant of this matrix must be 0. The determinant of this matrix must be 0. So this is the criteria that we use. First, we form this structure stiffness matrix, by applying the procedures. Then when we come finally to the structure stiffness equations, then in order to determine P critical, we make use of this criteria. This is the criteria that we have seen before also in slope deflection equation method. This is the criteria to get non-trivial solutions. So this is a mathematical process. So to get determinant of a matrix, this is a very tedious process. 2 by 2 is still manageable. 3 by 3 is becoming, maybe you need 10 pages or 3 or 4 pages of paper, and then it's a very tedious calculation. So this stiffness matrix method is actually suitable for computer applications. Okay, but for the purpose of understanding here, we bring you through the process of it. But for solving using hand it is, I think, very tedious and dealing with matrix, and it tends to mistakes. Okay, so this method is suitable to be put into a computer program. Now, the next thing what we want to do is to go through with you the process of getting this additional matrix, which accounted for the effect of axial force on the stiffness. The first one, the conventional one, I think we don't cover that. The conventional one, okay, this one, I think it is covered in many. It might also be already covered in your EAS661. Okay, EAS661, this is for bending. So this one, I assume that you already know how to get this. Now the next is to get this. Okay, to get the second one. This is P matrix K subscript 1ij. Okay, so this is the one that we would like to look at. And the basic idea here is based on this diagram. Okay, we get the element stiffness matrix. Then after that, by going through some standard procedures, you can get the structure stiffness matrix. So when we work with stiffness method, we always start with the element stiffness equation. Now, this diagram A and B shows in general a member which is subjected to axial force. Okay, member which is subjected to axial force. And the first diagram on the diagram A shows the element forces. Okay, so again, look at the coordinate system that we use for element. This is X and this is Y. So the positive direction for forces is in the negative to the positive Y direction. So Q1, this is a positive direction. Q3, this is a positive direction. And then for rotation is clockwise, Q2 at this end, Q4 at that end. And this axial force here that we are going to derive here is for compression. Okay, for compression. Then when this element is subjected to bending, at the same time it is subjected to a constant axial force, this is what happened to the element. So this is what happened to the element. There will be a deformations. Okay, the element will deform, and because you have bending and also you have axial force, then the corresponding displacement will be at this end delta 1 positive, at this end delta 3 positive, which is negative to the y-axis that we assume, and the rotations clockwise delta 2 at this end and delta 4 at the other end. Okay. Now, in order to derive this matrix, we make use of energy. Okay. First, we look at the external work done. External work done by the element N forces and also by this axial force. Okay. So here we have made assumption that this is small displacement problem, and linear elastic behavior. So in that sense, if we assume that this is a conservative problem, the sequence, whether we apply axial force first or there is a forces causing the bending first, the sequence is not important if it is linear elastic problem and small displacement. So the sequence that we are going to look at is we apply this axial force first. We apply the axial force first, P. So P is already there. Okay. P already applied there. Then there is a force causing the bending. So that is the sequence that we are going to look at. So P applied first. Then P applied first, so P there's a constant value. Then the member subjected to forces which cause it to bend. Okay. And with that kind of sequence, so the work done due to the forces, the element N forces acting, and at the same time there's a constant axial force acting, will be given by these equations. So this is W subscript E means the work done by the element N forces Q1, Q2, Q3, and Q4, and the work done by this constant axial force P. So here we are using the vector delta. This is vector delta. So vector delta means it includes delta 1, delta 2, delta 3, delta 4. All of them inside here. And this is transpose. And the second one, vector Q, represent Q1, Q2, Q3, Q4 inside this. Okay. So this is the work done. It is equal to half of Q1 multiplied with delta 1, Q2 multiplied with delta 2, Q3 multiplied with delta 3, Q4 multiplied with delta 4. Okay, and we can write it nicely in this way. Okay, this one means delta 1, delta 2, delta 3, delta 4 in vector form. If you transpose, it becomes a row form. So row vector multiplied with column vector gives you a scalar. So this represents half. Inside here is Q1 delta 1 plus Q2 delta 2 plus Q3 delta 3 plus Q4 delta 4. So this is what we write in compact form in this way. And remember, the axial force is already acting there. We apply the axial force first. And because axial force is acting at this end here. And later, this member will bend. This member will bend. So that when the member bends into this shape, so the axial force which is acting here is going to move. Initially, it is straight. Then it bends. So initially, it is straight. The P is already acting. When it is bent, so the P will move. The P will move certain distance because the member bend. And that distance is given by this half integration of these terms here. So this second term here represent the work done by this constant axial force because of the bending of the member. So if you pay attention to these terms here, it is very similar to the one that we use in Rayleigh-Ritz method. Only thing in Rayleigh-Ritz method, we take this as, with a negative in front, we take this as potential energy of the axial force. Yeah. If you can compare this with the potential energy of the axial force in Rayleigh-Ritz method, there's a negative in front. This is actually the similar expression. But here, we put plus here is because this one represents the work done by this constant axial force now. So this is the work done by external force. Now, we equate this to strain energy. We equate this to strain energy because the member bend. So there will be a bending strain energy stored in the member, and it is equal to EI over 2 because EI is constant here. Our EI is for constant EI over 2 integration. So this one you are familiar with. This is in the strain energy for bending deformations. So external work equal to internal work, which is equal to strain energy. So this is the starting equation that we use. And because of that, this is actually stiffness matrix is actually an energy method. Okay. Now, here there is a half here, there's a half here, there's a half here. So this one we can factor out the half. Okay. And we maintain this on this side, and this one moves to the other side. This one moves to the right hand side. So we come up with this equation here. Okay. Now, there's a K here. There's a K matrix here. And we want to change this into the form that we can know what is the K matrix. We want to change this because the left-hand side has a K here, which is pre-multiplied with delta transpose and then post-multiplied with delta. So here, if we can change this into something like this, then we can know what is a K. And from there, we know what is this stiffness matrix that we want to derive. Okay. So to do that, how do we get K? So we must do something to this side here. Okay. Now, in stiffness matrix method, we try to represent the Y, which is the deflection, the lateral displacement in terms of, we represent them in terms of a function which involves displacement at this end and also displacement at that end. That means we try to approximate the deformed shape Y using some functions that later we can relate it to the displacement at this end and displacement at the other end. So that is the things that the idea behind. And once we get Y in terms of displacement at this end and displacement at the other end, then we differentiate that, we can get this, and we differentiate 2 times, we get this. Then we can do the integrations, and then we can change this right-hand side into something like this. So in the process next time I'm going to show you, you will see that how this delta will appear on this side here. Okay. So this is the steps that we have to go through, meaning that we have to represent Y. Okay, what is Y? Y is this deformed shape. This is Y. Okay, what is the function representing this? Okay, the function representing this, we assume this function to be a cubic function. It is a cubic function. Okay, then by relating this displacement Y to what happened at one end and what happened at the other end. What happened at one end is when the Y at x is equal to 0, we have this one, and the Y prime is this. When x is equal to L at the other end, we have Y this, and the Y prime delta 4. Okay, so by assuming the function Y in terms of a cubic functions and making use of what happened to this function at one end, and also what happened to the rotation at one end, and what happened to the function at the other end, which is relate them to delta 3 and delta 4, we can write down Y in terms of these equations. This equation means this one multiplied with this plus this one multiplied with this plus this one multiplied with this plus this multiplied with this. This equation is we write in a row vector multiplied with the column vector. This actually comes from the equations y equal to this multiplied delta 1 plus this multiplied with delta 2 plus this multiplied with delta 3 plus this multiplied with delta 4. Then we rewrite them in this form because we want to make this appear here in vector. So delta 1, delta 2, delta 3, delta 4 will become vector delta. So this is y. Then we need y prime and we need y double prime. Why we need y prime and y double prime? Because in this equation here, you have y prime and y double prime. Y prime means dy dx. Y double prime means d2y dx2, which is needed in getting the strain energy. This is needed for these terms here. So once we know what is y, we can differentiate once to get y prime, and we can differentiate y second time to get this equation. So this C here is a row vector, and each one of it is, you differentiate this one time, you get the first one. You differentiate this the second time, you get the second one in this C row vector. You differentiate this one respect to x, you differentiate this respect to x, you get C. Then you differentiate this C one by one again, another one more time, or you differentiate these two times, then you get D. Okay, and that delta remain because this delta is nothing to do with the x. So if you substitute this into this here, then you do the integrations. If you do the integrations, and also you substitute the one for y prime into this. This is a square here, and then you integrate them one by one inside there. Okay. Finally, we are going to get the K matrix. We are going to get the K matrix, which is this matrix here. This side here will be changed into something like this. And then from there, if you substitute this and also this into the equation just now that I show and do the integrations, then finally we come to this outcome here. This is the stiffness matrix, considering the effect of axial force on the stiffness. So this is the conventional one, and this is the one that accounts for the effect of axial force. Okay, and it is also symmetry, meaning that whatever you have here is the same as the column, the second row same as the second column, and so on. And this has a special name called initial stress stiffness matrix. So this matrix that I show you here, it can be used to analyze a beam column, which means there is parts which accounted for the effect of force causing bending. This is a conventional stiffness matrix for bending, and this accounted for there is axial force acting. So this can be used for beam column. Yeah. Which one? This one, Y. Okay. Y actually comes from, if I can show you here. This is in chapter, let me see, chapter 1. So this is section 2.13. Actually come from here. Okay, let me see. Already. Now, this is where it come from. I think if I can, this is a bit, okay. If you look at this particular, okay, it's a bit not so clear here. So this equations is the one that I show you on the slide, 2.172. The y start, we start by assuming the y in this form, which is y is equal to a cubic function. Y is a cubic function, which is y is equal to a constant a plus bx plus cx squared plus dx cubed. So that is a cubic function that we assume. Then we make use of the conditions. When y, what happened to y and y prime when x is equal to 0? And what happened to y and y prime when x is equal to L? So we have these four conditions. We can determine what is A, B, C, and D. So once we use this to determine A, B, C, and D, okay, it first become like this. It first become like this because it will be in terms of delta 1, delta 2, and something with, and also x there, okay? So it comes from here that we assume cubic function. We need to assume as cubic function here because at least we can, I think, simulate the condition of constant shear. Okay. So we need, for beam bending problem, the function that we need to assume is at least cubic. So start from here, applying this thing, come from this. Then rearrange this in terms of a function multiplied with delta 1 plus a function multiplied with delta 2 plus function multiplied with delta 3. So that is where we get into that form. From here, which we apply this condition to this, then we rearrange that, collecting all the terms to multiply with delta 1, something multiplied with delta 2, something multiplied with delta 3, and this is how we get that. Okay. So this is actually the process of getting that. Because what we want here is y represent in terms of a function multiplied with the nodal displacement. Okay? And another way is, the other important thing is how to turn this side into something like this is given in here. So it is shown here, y prime, y double prime, and this is the content of C and D. And, okay, because y prime, this is not clear here, sorry, y prime is C delta, y double prime is D delta, and y prime square, it can be written as delta transpose C transpose multiplied with C delta. Y double prime square can be written as delta transpose D transpose. You transpose this whole thing, multiply it back with this, you get y double prime square, y prime square. So with this, you substitute here, okay? And this delta and delta is not a function of x, so you can factor it out. So when it comes to here, we make it into the form which is similar to this side. There's a delta transpose, there's a delta transpose, then there's a delta at the end there, and the center one here is the k. Okay, the center one is the k. So k is actually this. K is equal to here that you need to integrate this D transpose multiplied with D, and all these are functions of x, so you need to integrate one by one. This is the matrix. And the same thing, C transpose, which means you change this into column vector, multiply with a row vector, then you get matrix. You get a matrix, 4 by 4 matrix, and integrate each one of them one by one, respect to x, and the outcome will be like this. That is the outcome that I show you. After you integrate this one, you get this. You integrate this thing, you get this, and there is a multiplied with P in front here. Okay. So to answer your question, Metam, that is where it comes from, the thing. Okay. So if you refer to the detailed pages of that thing, you can get the process, okay, the detailed process of it and also the explanation. So this is the basis of the equations that we are going to use, and you don't have to memorize these equations. I think these equations, if you are given these kind of questions, this equation will be given to you. Okay? Just remember that if there is a beam member in the problem and there is no axial force, then we only consider this part. If there's a problem there and it is a column member and there is axial force present in that member, then we have to add this part. So if it is a beam member only, then we don't need to consider, which is P0. There is no axial force P. Okay. Now, if we refer to, now this is a matrix 4 by 4, and as I mentioned, calculation matrix using hand is very tedious. So for hand calculations, to make it easy, it is better to have everything inside here numbers only. Here you have L cube, L square, L cube, L square, and here you also have L, L, L. So to get rid of this L cube, L square, to make it only numbers, so we can rewrite this and make it into something like this, okay? But here they are easy for hand calculation because these are numbers only, multiplied with some common terms in front. L is not inside, L is taken outside here. And this is the length of the member, length of the element, okay? Here also, the L which is inside here already taken them out. Okay? But here, instead of element forces, which instead of forces, rotation, forces, forces, bending moment, forces, moment, we change it all into forces. So by the process to get this is you have to change this second one and the third one, the fourth equations, dividing by L first, dividing all the equation with L, and then after that, multiply the second. We have to get these terms multiplied with L. Okay. Now, this, if you are being asked to solve problem using stiffness matrix equations, you will be given either these equations, this set of equations, or this matrix. They are the same, okay? But for hand calculations, it changed into this form. So either form of this matrix will be given to you, and you have to know how to use it. So the L here is the length of the element. Okay. So if the length of the element is different, then this L has to be used, the corresponding length of the element. If the element is not subjected to axial force, this term no need to consider. If the element is like a column and then subjected to axial force P, then you have to consider this. Okay. So this is the basis of stiffness matrix method. Okay.